All right, good evening and welcome to lecture number 15 for MT225. Last time on Monday night, we looked at truss analysis by using the method of joints, and we're going to practice with that tonight. I'll work through step by step another problem, and then we'll go into our practicum session. Maybe I'll do one more small example problem, and then we'll go into our practicum session. I'll give you a couple of trusses to work out. Um, and there is a homework assignment posted that is all about method of joints. So we'll get some practice there as well. So let's see here. Homework 6 posted to do next Wednesday. So March 31st. So tonight, more practice with method of joints. So a little review on the method of joints. The procedure for the method of joints is to first solve what I call the external problem. And if you're still feeling a little shaky on the external problem, go back to lecture 12, watch that video, work through the examples there, make sure that it makes sense. Because if you screw up your solution for the external problem, all your work in doing method of joints is going to be wasted. So we've got to find those reaction forces at the supports. Then we use the fact that if a structure is in equilibrium, then every piece that makes up that structure must also be in equilibrium too. Specifically, the joints that connect the members of the structure together have to be in equilibrium. So we isolate each joint as a free body, as its own system, and we look at the forces that are acting on it. When we draw our free body diagram, we'll find that we have two unknowns, and we can solve for two unknowns with our equations of equilibrium. The sum of forces in the x direction equal to 0, and the sum of forces in the y direction equal to 0. So we can form our equations of equilibrium and solve for our unknowns. And through that solution, we'll figure out how much force each member of the truss is carrying, and we'd find its state, whether it's in tension, in compression, or if it's unloaded. This is an iterative process, so it's something that we are going to have to repeat several times to solve everything. Last time I gave you a basic rule of thumb that says that if you have n joints in the problem, n pins holding the structure together, you're going to have to do steps 2 and 3 n minus 1 times. So if you've got 4 joints in the truss, you're going to have to do 3 free body diagrams. If you've got 10, you'd have to do 9 free body diagrams. So we need one fewer setup, one fewer iteration through 2 and 3, steps 2 and 3, for then the number of joints that we have in the truss. And so we keep on repeating. We loop over this until we have everything we need to know. So we've learned everything there is to know about the truss, and then we summarize it. We draw out a force summary diagram. Now, the math isn't that hard. There's some sines and cosines, there's some inverse tangents to get angles, all skills we have, all skills that we've worked on. Probably the part that gets most confusing and the part that I usually see people messing up is figuring out whether a member is in tension or in compression. And there was a pretty lengthy discussion about that in lecture number 14. So if you need some review on that, go back to lecture 14 and look at that. I will summarize the results of that discussion here, that essentially we're looking at our forces sort of in a mirror. We're looking at it through the mirror of Newton's third law. Newton's third law says that when we exert a force on something, that same force gets exerted back on whatever is doing the exerting. So we have two forces. If we're not clear which one we're looking at, it can be very difficult to interpret whether something is in tension or compression. People always want to think about the force on the member, but we're solving for the forces on the joints. Those are reflected. They're Newton's third law, reaction forces to the forces on the members. So it's backwards. It's counterintuitive. And I drew this last time as a way of at least giving you a tool that you can use to compare against your drawings and get the right answer, whether something's in tension or compression. And the thing to understand looking at this drawing is that I am not showing forces. Those arrows aren't forces on the member. They're forces on the pins that are holding the members together. The kind of lately outlined member is just sort of a ghost image of it, just showing you where it is. It's not really part of the system. When we do method of joints, we look at the joints, we ignore the members. We're seeing the forces on the joints due to the members. And the first picture, that top picture, I know you want to say it looks like it's squeezing that member together, so it looks like compression, but it's not. It's tension. And the way to think about it is not to think about the forces on the member, it's to think about the forces on the joints. Imagine those pins, those shaded in circles in the drawing, in the top drawing, are nails driven into the wall. If I took a big rubber band and I stretched that rubber band out and hooked it onto those pins, onto those nails, wouldn't the force on those nails be toward each other? They'd be pulled in. But I think everyone would agree that rubber band's in tension. When things are in tension, they tend to pull their supports inward. Only things in tension can shrink and go back to a smaller size. So what we're looking at in the method of joints are the forces on the supports, on the pins. And in tension, the pins are drawn inward. So that top picture illustrates tension from the point of view of the pins. Correspondingly, the bottom represents compression. Only a member that's in compression can push its supports outward. Only something in compression can spring outward. So if you think about compressing a spring and then wedging it in between two supports, those two supports are going to be pushed apart. Compression pushes things apart. Tension pulls things together. So that's how we interpret tension and compression. So if you have some concerns about that, if you're not 100% clear on it, I don't expect you to be 100% clear on it just yet. It won't be until you practice this perhaps dozens of times to be able to really get it. But in the meantime, you can use this picture, compare it to what you've got out of your free body diagram, and interpret it correctly. Get the right answer. The understanding of that right answer will come in time. So let's work through a problem. So here is a truss problem. This is similar to the one that I worked in the practicum session last time. It's switched around a little bit. It's a little different. That cross member is in a different different position. It's a diagonal from left to right up instead of from left to right down, and that changes things. So this will be the truss we'll analyze as our first example, and then if there's time, which there should be, I'll do another example. So first thing we're going to want to do is draw the truss and do the external problem. Solve for the reactions at supports A and B. So first thing I'm going to do is just quickly copy this down to my page. When we do the external problem, we really don't care about the internal structure of the truss. In fact, in my drawing, I'm not even going to draw a member AC or any of that internal detail because it doesn't matter for the external problem. This might as well just be one big chunk of material that's 10 feet wide by 6 feet high. So we don't really care about the internal structure for the external problem. So I'll copy over my forces here, 10 kips. We've got 4 kips and 5 kips. And let's see our geometry. Got 6 feet high and 10 feet wide. All right, so let's take a look at that. So there's the truss, and I've eliminated the internal detail because it doesn't matter for the external problem. So we're into step 1 here, solving for the reactions at the supports A and B. So the first thing we really need is a free body diagram. And in the external problem, our system is the truss. So the truss is the universe. It's everything we care about. And we're just looking at what touches the edges of that. So there's our truss. We have a support at A that's a pinned support. So that generates two reaction forces, RAX and RAY. We have at B, we have a roller. So that'll be RBY. And we've got our externally applied loads, this 5 kip side load, 4 kips pushing down there, and 10 kips there. We can define our coordinate system. So there we go. So let's go ahead and solve this. Fortunately, this is pretty similar to what we've already done with beams on supports. So you've already got the math for it. We're going to come up with 3 equations. Sum of forces in the x direction equals 0. Sum of forces in the y direction equals 0. And sum of moments about a point equals 0. So let's write those up here. So sum of forces in the x direction, we've got a positive 5 kips, and we've got a positive RAX. Nothing else in the x direction to deal with. We'll do our sum of forces in the y direction. We've got a positive RAY, positive RBY. We've got a minus 4 kips and a minus 10 kips. So there's our sum of forces in the y direction. Now we need our sum of moments about a point, and I'm going to pick point A as my pivot point. So my sum of moments about A. Now be careful with the moment equation. This is where I see people make most of their mistakes. They usually are okay with their sum of forces in the x and y directions. It's the moments that cause the most problems, and you've got 2 big issues with moments. First, making sure you've accounted for every force that generates a moment, and secondly, making sure that you have the right arms for each of the forces. So let's first figure out what forces are going to generate moments about A. Only forces that have lines of action that are not running through A will have a moment. So RAY and RAX, they push on the pivot point, so no moments there. Also, this 4 kip force over here, its line of action shoots right through the pivot point. So as far as the moment's concerned, it may as well just be pushing right down here. So it doesn't have a moment. So this 4 kip force does not have a moment. The 10 kip force, on the other hand, does. The line of action is definitely not running through A, so that will have a moment. RBY similarly has a line of action that doesn't run through A, so it'll have a moment. Now, the force that most people initially, when they first start working on these problems, miss for a moment would be this one, because we're so used to the forces pushing down from the beam problems and having those cause moments. But we're not so used to having horizontal forces causing moments, and they do, as long as their line of action is some distance away from the pivot point. In the beam problems, the arm was so small because the beam was so thin, we never had to worry about horizontal forces causing moments. But here in a truss, we've got feet of arm here, so it's definitely going to cause a moment. So that 5 kip force, the arm for that is going to be the distance from the pivot point. So the perpendicular distance from the pivot point, the distance between the line of action and the pivot point, that is our arm. So definitely the 5 kip force will have a moment. So we have 3 forces here that are going to have moments. So we should have 3 terms in our moment equation. So let's take care of the 10 kips force first here. That 10 kip force has an arm of 10 feet. Remember that we determine the arms by looking at the distance between the line of action and the pivot point measured at 90 degrees. So how close this arrow gets, if this arrow flies along its line of action, how close will it approach A? Well, the closest it ever gets is 10 feet. So that's its arm. So we have 10 feet times 10 kips, that's 100 kip feet. If we're pinned at A and we push down over here, that should generate a clockwise moment, and clockwise moments according to our coordinate system are negative. So that's negative 100 kip feet. Then we have this 5 kip force, same idea. Look at how close that arrow would get to A if it's put anywhere along its line of action. And the closest it would ever get is right where it happens to be, 6 feet away. So our arm is 6 feet, the force is 5 kips, so we have 6 times 5, 30 kip feet. If we pin at A and we push to the right up here, we get a clockwise moment, and clockwise moments are negative. And then finally, we've got RBY. This is where the second big mistake comes in with solving the moment equation. People tend to write just RBY. And they might even say, well, it's positive, so positive RBY. It's a small mistake, but it's enough to throw everything off. What's happened here is you've forgotten the arm. Every term in here has to be a moment, not a force. And moments are arm times force. So we have to figure out the arm for our unknown force, RBY, and that arm is the same as the arm for the 10 kip force, 10 feet. So it's 10 RBY. And it is indeed positive. If we pin at A and push up at B, we get a counterclockwise moment. And counterclockwise moments are positive. So there we've got our 3 equations of equilibrium. Now, since the system is in equilibrium, these sums must all equal 0. So there we've got our equations. Now, the first equation we can solve pretty easily. RAX is a negative 5 kips. And that negative is a clue that we made an incorrect assumption with respect to RAX. When I drew my free body diagram, I assumed RAX was pushing to the right. But it can't be pushing to the right because this 5 kips is also pushing to the right. If both forces push to the right, then we don't have equilibrium. We have this thing going off to the right. We have a net force. So the math is telling me here to be in equilibrium, we've got to have RAX opposite the direction it's in. The negative doesn't tell us necessarily that it's going to the left. It's all based on whatever assumption we make. When a negative shows up, it really means it's opposite whatever you assumed. So sometimes we have to make guesses. When we make those guesses incorrectly, the math will tell us by throwing a negative in our answer. And we have to stick with that until we redraw the system. So RAX is negative 5 kips. We can't do anything with the y direction equation just yet because we have too many unknowns. We don't know RAY or RBY. But the moment equation we can work with a little. If we combine the negative 100 and the negative 30, we've got negative 130. And solving the equation, 10 RBY equals 130. Divide both sides by 10. And RBY is 13 kips. So RBY 13 kips. That's a positive answer. So we know we got our assumed direction correct. And now that we know RBY is 13 kips, we can go up here to the y direction equation and plug that in. So we have RAY plus 13 minus 4 minus 10. That gives us RAY minus 1 equals 0, which gives us RAY is 1 kip. So there we've got our reactions. We have the reactions at the supports, and that's the first step to doing the truss analysis. We've got the external problem solved. Anyone have any questions on our solutions for the external problem. All right, so let's take it a step further here. To go further, we now have to go into the internal problem. The first step in working with the internal problem is to redraw your truss with the support forces in. So I'm going to redraw this so I have a nice clear picture to look at. And I'm going to draw the internal structure too. And let's see, that had, yep, that went up and to the left here, or up and to the right. So we have A, B, C, and D. At A, we've now figured out exactly what's going on. We have 5 kips pulling to the left, and we have 1 kip up. So rather than drawing the little triangle there, I'm going to draw in the forces that we are supplying from that support. And then we've got 13 kips over here. We had 10 kips down. We had 4 kips here. And we had 5 kips there. So that's everything going on outside the truss. We also had our geometry. We had 6 feet and 10 feet. So there we go. So to figure out what's going on inside the truss, what each of these members carries, and we've got several members to work with here. We've got 1, 2, 3, 4, 5 members to work with. So we need to figure out in the truss analysis, we need to figure out everything there is to know about the truss. That means the loads carried by each of those 5 members and the state of tension or compression for each of those 5 members. So the way we usually note that is with a table. So we'll build up our table here. That table usually has 4 columns to it. And this one's going to have 5 rows. 1 for each member. So this will be where we label our members. We're going to put the load in kips here. And then I usually label these T and C for tension or compression. Doesn't matter what order it's in, compression, tension, tension, compression. If I really cared about it, I'd give you the table to fill out, but you can note it any way you want, as long as it's clear. When we fill in the table for the members, though, standard practice is to go in alphabetical order. So we start at A. The first member is going to be AB. The next one's going to be AC. Then AD. When we run out of members connected to A, we go over to B. We already have AB in there, so don't label it again as BA. We always want our member names to be in alphabetical order. But I don't have BC in there yet. Jump over to C. Well, I've got AC, I've got BC. What I don't have is CD. So we'll have CD there. So that's all 5 members. Now, in the method of joints, our job is to pick a joint, draw its free body diagram, and then work through the analysis, solve for the unknowns. When we draw the free body diagram of a joint, what we end up with is a concurrent force system. All the lines of action intersect at one point. And that type of problem we learned a few weeks ago, we only get 2 unknowns. We get 2 equations. The sum of forces in the x direction equals 0, and the sum of forces in the y direction equals 0. So we can't pick a joint. We can't start at a joint where we are missing more than 2 pieces. So for example here, if we started at A, we could draw the free body diagram, but we'd end up with 3 unknowns because we don't know the force carried by member AB, we don't know the force carried by AC, and we don't know the force carried by AD. That's too many unknowns to handle with 2 equations. 2 equations, we can only have 2 unknowns. The moment equation doesn't work here because nothing has a moment about A. Nothing touching A has a moment about A. So all we'd ever get if we tried to do the moment equation would be 0 equals 0, which is true, but unenlightening. So we have to jump to a different member, a different joint. C isn't going to work either for the same reason. C has 3 unknowns at it. So we could go to B or we could go to D. And B looks slightly easier to me, so I'm going to start there. The way we draw our free body diagram is the same way we've drawn all of our free body diagrams. Draw a little circle around what you're interested in. Anything that touches that circle or crosses that circle or penetrates that circle has to be represented in the free body diagram. So down here, I'll draw the free body diagram for joint B. So first, got to draw the joint. Well, there it is. Now, joint B has 3 forces acting on it. One of them is from our support. And when you draw your free body diagram, you should always start with the forces you know. And when you know forces, you know their magnitude and you know their direction. Draw it so the tail of the force is at the joint. No heads at the joint. So instead of drawing this pushing up on B, I'm going to draw it pulling up on B. So there's my 13 kip force from my reaction from my support at B. Then there's the force due to member BC. We cut through that right here. Now we've got 2 choices. Either that member BC is pulling on joint B, so the force is upward, or it's pushing on joint B, so the force is downward. Based on what we've already drawn here, it's a lot easier to draw a downward force. It's a lot clearer to draw a downward force, so we're not drawing it right on top of the 13 kips. So that's how I'm going to draw that one. I'll say this is the force due to member BC. And that's usually how we label those, FBC. And then we've got member AB. Member AB is over here. And again, we have the same choice. We don't know necessarily whether it's pushing on B or pulling on B. So it's our best guess. The math will tell us if we guessed wrong. So it's not really worth putting a whole lot of effort into thinking about what direction it's in. If it's not immediately clear, guess something, move on. The math will tell you what the answer is. So I'm going to guess that it pushes to the right. So that would be the force due to member AB. I'm going to redraw this here. I'm just going to put this down here so it's a little clearer. Force due to member BC. So there's my free body diagram. Now, if you're thinking about it a little bit, you're looking at that free body diagram, remember what we're looking at is equilibrium. And you might be looking at that and saying, there's no way that can be in equilibrium, because it doesn't look like equilibrium. Equilibrium's got to look like a tug of war, no one's winning, where all the forces cancel out. And here it looks like we've got an unbalanced horizontal force. Well, there is one way that can still be equilibrium, and the math will tell us that if you can't see it immediately. So let's work through the math and we'll see what it tells us. First, we'll draw our coordinate system. No need for a moment here because there are no moments. All the forces have 0 arm about joint B. But we have our sum of forces in the x direction and our sum of forces in the y direction. Now in the x direction, all we've got is FAB. No other forces in the x direction. In the y direction, we've got a positive 13 kips. We've got a negative FBC. Now, since that joint is in equilibrium, the sum of forces in the x direction must equal 0, and the sum of forces in the y direction must equal 0. It's the only way it can be in equilibrium is if the net force in both directions is 0. Well, that tells us our issue here with member AB. The only way this can be in equilibrium is if member AB doesn't have a force on it, if member AB is unloaded. So member AB is unloaded here. Otherwise, if this was some force other than 0, there'd have to be something else counteracting it, and there's nothing there. So member AB is unloaded. So we can go up to our table and write the load is 0 kips. for member AB. Now, that doesn't necessarily mean that it's going to be unloaded in all situations. It's the first thing you might think if you're trying to be an efficient engineer and say, well, I can build this with less material now because that member doesn't carry any force. And that might be true if this is the only kind of loading you can possibly have on it. But if the loading's a little different, if there are different loads in different places, that member might carry something. So you can't just cut it out because one loading shows that it's unloaded. It's a little bit more of an analysis to figure out if it's something we can eliminate from the design without impact. Now, a member carrying no load isn't in tension or in compression. So what I do there is I just kind of draw lines through there. It's not tension, not compression. Now, member BC, that one definitely does have a force on it. If we solve this equation, hopefully not too hard, FBC comes out to be 13 kips. So the load carried by member BC is 13 kips. So we can go up there to the table and fill that out, 13 kips. And you'll notice I'm not writing units here. The units are labeled in the table, in the header. So it saves some space, saves some work. You don't have to write the units down if the table header has the units in it. But as far as which box check goes, 13 kips is pretty easy to get, but which is it, tension or compression? Well, to figure it out, the first thing to do is to go back to your free body diagram and compare it to the original drawing of the truss. That'll give you some idea of where the member is compared to the joint. So joint B is here. So it's at the center of our free body diagram. Member BC is above joint B. So I'm going to come down here and I'm going to sketch in member BC. So there in red is member BC. And here is the force that member BC is exerting on joint B. Don't get confused with this other force here. That's just the reaction force from the roller. That's not something that we're looking at to determine whether this is in tension or compression. It's always the member and its force as shown in the free body diagram. So this is member BC. Down here is its force. Our answer over here came out positive, which means our direction's good. Member BC is pushing joint B down. And so we have to figure out whether that's tension or compression. So at least at first, you should copy over that slide that has the tension or compression drawings on it. A little sketch just to show what that says. We've got our joints pulled together. That was tension. Joints pulled apart or pressed apart, pushed apart like that. So really emphasizing that it's the joints we're looking at here. That's compression. In these types of problems, in method of joint problems, compression is shown by pushing the joints apart. Only a member in compression can push its supporting joints apart because only something in compression can spring outward. Only a member in tension can draw the joints together because only a member in tension can shrink back to its original size. So we'd have to compare which one do we have here? Well, here we've got the joint pushed away. It's pushed outward. We have compression. So member BC is in compression. And that's not too hard to expect physically. If you look at the free body or you look at the drawing of the truss, you've got 10 kips sitting right here. You got 10,000 pounds pushing down on joint C. You've got 13,000 pounds pushing up at joint B. Well, that's going to definitely squeeze this thing together. That's definitely going to put this into compression. So it makes sense that we should get compression. The skill, though, is seeing that we've got compression when you're looking at this mirror image of the force in the member on the joint. So that's joint B. And we netted 2 forces. We knocked out 2 lines in our table. We got 3 more to go. And in order to figure it out, we've got to go to another joint. We've learned everything we can from joint B. And generally, if you can work out joints that only deal with members at 90-degree angles, life's a lot easier. So while C comes next in alphabetical order, I might be encouraged to jump to D, because at joint D, all I've got are 90-degree angles, which means no sines, no cosines, just sums in the X and Y direction. So I'm going to go and jump to joint D here, and that'll be our next free body diagram. So the free body diagram at joint D. So again, go back up to the joint, draw a little circle around it, make sure you account for everything that touches that circle. Cuts through 2 members, member AD and member CD, and there are 2 forces acting on it. So we'll draw the free body diagram starting with the joint. So there's joint D. We've got 2 known forces. We've got a force to the left at 5 kips and a force down at 4 kips. Putting the tails at the joint, that'll be 4 kips down and 5 kips to the right. Now it's a little clearer how to draw our unknown forces in. We've got member CD horizontally. And again, it's a guess. Does it push or pull? Well, go with what's easiest to draw in the free body diagram. Because it's if you draw your free body diagram in a confusing way and that causes you to mess up your equations, then what's the point? You might as well draw it in a clear way and risk getting a negative answer that but getting the right equations, than draw it in a confusing way and leads you to miss a force or to get the wrong equations. So this will be the force due to member CD. And then we have member AD. I'm going to assume member AD pushes up on joint D. So there's my free body diagram for joint D. Got our coordinate system. And we can do our sum of forces. So we've got the sum of forces in the X direction. Well, we've got a negative FCD and a positive 5 kips. And we've got our sum of forces in the Y direction. We've got a positive FAD and a negative 4 kips. We're in equilibrium, so both of those sums have to equal 0. And they're both pretty easy to solve. Again, no sines, no cosines. The equations are completely separate from each other, so there's no mixing of unknowns between equations. So pretty easy to solve. Be careful with your negative signs. Don't introduce something incorrect or jump to a conclusion by trying to solve it by inspection rather than working it out. But FCD will come out to be a positive 5 kips. And FAD is a positive 4 kips. So we got both of those right. The assumed directions are good. Member CD carries 4 kips. Carries 5 kips. And member AD carries 4 kips. So we can fill those in the table. But we still have to figure out tension or compression. So let's work with AD first. So look at the free body diagram. That's for joint D. Member AD is below it. So member AD is over here. So member AD is below joint D. There's the force that member AD is exerting on joint D, and that's pressed outward or pushed outward. That's compression. So member AD is in compression. Member CD Well, if we go back to the drawing, member CD is to the right of joint D. So member CD is over here like that. And member CD is pushing joint C or joint D away. So matches up here with the left end of my compression beam. So this is also compression. So member CD is in compression. So far, everything we've looked at is in compression, which is rare, but just has to do with how we've loaded this and how the order I've worked things in. That's all we can learn from joint D. We netted our two unknowns at joint D. To figure out what's going on with member AC, we either have to go to joint A or joint C. We have to go to one of the two joints that touches member AC. So that'll be our next step, is to pick another joint to work with. Well, I usually make a call on that based on essentially how many arrows I'd have to draw. And it's kind of a toss-up in this one. In the free body diagram, if we would draw the free body diagram of A, well, it looks like 5 because we have 1, 2, 3, 4, 5 forces there. But remember, AB is unloaded. So physically, it doesn't exert a force on A, so we could throw it out. So there are only 4 that I'd have to draw there. If I go over here to member C, or to joint C, I've got 4 forces there too. So it's really the same amount of work no matter where I go on that. When that's the case, I usually like to err on the side of things that are given to me rather than things I've calculated. So I calculated this 1 kip and that 5 kip, and there's a chance that I'm incorrect there. So if I work joint C, I'm a little bit further away from the stuff I calculated and closer to the more pure information that was given to me in the problem. So joint C looks like a good candidate to start with here. And I would challenge those who are watching this on video later to go back and work it at joint A and see that you get the same exact answer. See how the free body diagram comes out different, but you still get the same answer. So let's work with joint C. So if I draw my boundary around joint C, draw the free body diagram, there's the joint. I've got 10 kips down, so I'm going to draw that like that. Tail at the joint. Always start with what you already know. Leave the unknown to last, because then you get a better chance of drawing it in the right direction. We know everything else there is to know at joint C except what's going on with AC. Member BC is down here, and member BC, according to our table, carries 13 kips in compression. So it's again important to get the direction right, because these arrows are the directions you're going to draw on your free body diagram. So member BC is in compression. That means it's pushing joint B down, but it's pushing joint C up. So the 13 kips that comes from member BC has got to be up. So that's 13 kips there. That comes from the fact that member BC is in compression, and members in compression push the joints apart. So B is down, C is up. We've got member CD. Member CD carries 5 kips, also in compression. So in compression, joint D is pushed to the left, but joint C is pushed to the right. So to properly represent the force due to member CD in the free body diagram, I've got to draw it to the right. So, and there's no guessing there or anything like that. It's known. We just have to write it correctly in the free body diagram. So 5 kips to the right. So that's everything we know at joint C. Now we need to add in member AC. And now it's pretty clear what direction member AC should be in. Member AC is going to have to be down and to the left. It's the only way this can be in equilibrium. If we drew it up and to the right, the other option, everything would be to the right, and we'd have an accelerating truss. We wouldn't have a static truss. So the force due to member AC must be down and to the left. Now, in order to solve the problem, we are going to need an angle. We need this angle right here. Well, fortunately, that's the same as this angle right here. And we can figure out that angle by using a little bit of trigonometry. We have a right triangle here, just like that. And we can find an angle by finding the inverse tangent of opposite over adjacent. Well, the opposite side is 6 feet. The adjacent side is 10 feet. So we can go over to the calculator and do inverse tangent of 6 over 10. And that's 0.6. 0.6 is 6 over 10. Inverse tangent, 30.964 degrees. So that's the angle here, 30.964 degrees. And here I'm arbitrarily keeping 5 sig figs. We'd make that call based on whatever we're given in the problem that tells us what angle to, or what we want in our answer. So here I'm assuming my answer should be good to 3 sig figs, about the minimum that I'd accept as being good too. And here we're keeping 2 more sig figs. So 30.964 degrees. And notice here, this is the third joint we're working. We only have 4 joints total. This is the last one we should need to work out. And then the last joint, we only end up with 1 unknown. That's how it usually works out in these problems. So we only end up with 1 unknown here. So we only need 1 equation. Sum of forces in the x direction or sum of forces in the y direction. And since I only have 1 other force in the x direction, I'm going to go with the x direction here. You could do the y direction, you'd get the same answer, but sum of forces in the x direction. We've got 5 kips to the right, and then we've got something to the left. We've got a piece of FAC. We have the adjacent side of FAC. Adjacent goes with cosine. So we have FAC cosine of 30.964 degrees. Well, that equals 0. And that's not as easy of an equation to solve as we had before, but it's still an equation that's not too bad. If we add FAC cosine of 30.964 to both sides, we get 5 equals FAC cosine 30.964 degrees. If we divide out the cosine, we'll get our value for FAC. So FAC is 5 divided by the cosine of 30.964. And that gives us 5.8310. So 5.8310 kips. And it came out positive, which means our assumed direction is correct. So we can go over to our table here and fill in 5.8310. We have to determine tension or compression. So go back to the free body diagram and sketch in the member. Here's joint C. Member AC is down and to the left. So member AC is like that. Well, we'd have to go back to the picture here and see which one that looks closest to. Well, it looks like tension. Member AC is pulling joint C in toward the middle of the member. That's tension. So member AC is in tension. And there we go. We've got the problem solved. Now to communicate our answer, it's a good idea to draw a force summary diagram. And the force summary diagram, it's usually a good idea to draw it as big as you can, because cramming it into little spaces on the page can be problematic. But that's where you put everything that you've calculated. Some people get fancy with it and draw different colors for the applied loads and the internal and external loads, but you don't need to do that. This is also a good place to round to your final number of significant figures. So first I'll draw in my applied loads and my reaction forces. So there's that, and 13 kips. And now I'll fill in the table. So member AB carried no load. So member AB, I just write 0 kips there. Not a bad idea to label those. Member AC carried 5.8310, rounding that to 3 sig figs. It's 5.83 in tension. So 5.83 kips. And then in parentheses, I'll put T. That'll tell me this is in tension. Member AD was 4 kips in compression. And so I've got 4 kips with a parentheses C. Member BC carries 13 kips, also in compression. And member AD carried, oops, I labeled something wrong here. Member CD, there we go, is 5 kips in compression. So that's our force summary diagram. That'd be a fine final answer for our problem. So would a table. If you redraw the table, round it to the right number of sig figs, that'd be a perfectly fine answer too, as long as somewhere else you've got your reaction forces written down. We want to communicate everything that we've learned about that truss in one picture. So that's a truss analysis. That's method of joints. Any questions there? All right then. Well, let's set up another problem to work on. And I've got enough time to do one more example. So let's do one that looks a little different than anything we've drawn out here yet. Let's take something that is on a wall. These wall problems come up a fair bit. So we'll draw a something that looks, let's say like that. Some sort of triangular structure. I'll put a pinned support here and a roller here. And this is sitting up against a wall. The little fringes here mean some sort of solid structure. And I think I'll hang on this a 20 kips load. We'll make this whole thing 12 feet wide. And I guess we'll make it we'll do something that looks sort of like this. That'll give us that distance there. And we'll do, let's say 2 feet and 10 feet. That looks pretty close to scale. And we'll label these A, B, and C. So we have a 3-joint, 3-member truss. And we want to find out everything there is to know about it. So in the end, we should have a table filled out. with 3 rows, one for member AB, one for member AC, and one for member BC. Loads are in kips, and tension or compression. All right, so let's take a look at this one. First thing to do is to solve the external problem, is to find the reactions at the supports. So I'll draw a free body diagram of the truss. So the free body diagram will look something like that with our 20 kips here. Up at the top, we've got a pin support at joint B. So I'm going to draw that as RBX and RBY. Down here at A, we've got a roller. And rollers exert a force perpendicular to the surface they're on. In most of the problems we've done, that surface is the ground. So it applies a force vertically, but here it's a wall. So it's applying the force horizontally. So that'd be RAX. And then I've got, let's see, I've got the members A, B, and C. And I've got the geometry, which we'll copy over here. So we've got 10 feet, 2 feet, and 12 feet. So there is our free body diagram for the external problem. And in the external problem, we have a non-concurrent force problem. So we have the sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point, all equaling 0. So let's write those up. So sum of forces in the x direction. We can draw our coordinate system in here just to keep things positive. So sum of forces in the x direction. Well, we've got RBX and RAX. Both of those are to the right, so they go into the sum positive. RAX plus RBX. Nothing else in the x direction. We can take our sum of forces in the y direction. We've got RBY up, so that's positive. And we've got 20 kips down, so that's negative. Nothing else in the y direction. And then we need moments about a point. And I think just for a change of pace here, I'm going to pick joint A, the non-pinned support. I'll pick the roller support here. So if you picked A or you picked B here, it'll work the same way. You'll get the same answers out in the end. So we'll pick A here. And if we're using A as our pivot point, we're going to knock out RAX for having a moment. RBY will also not have a moment since the line of action of RBY goes right through A. But RBX will have a moment, and the 20 kip force will have a moment. So we have two terms in our moment equation. And in order to build our moment equation terms, we need arms and forces. So we've got our pivot point at A. We've got this 20 kip force. The line of action of that 20 kip force is 12 feet away from A. So we've got 12 times 20, that's 240 kip feet. If we pin at A and pull down at C, we have a clockwise moment. And clockwise moments are negative. And then we've got RBX. Well, RBX's line of action is a little easier to see. It's also 12 feet, but it's 12 RBX. Pinned at A, pushing to the right, clockwise moment, so also negative. So there are three sums. Sum of forces in the x direction, sum of forces in the y direction, and sum of moments about A. Since the truss is in equilibrium, the sums must equal 0. Now the x direction equation we can't do much with because we've got two unknowns. But the y direction equation we can solve pretty quickly. RBY is 20 kips. Came out positive, so RBY must really pull up. And then we've got our moment equation. We can solve that too. If we add 12 RBX to both sides, we have 12 RBX equals negative 240. Divide both sides by 12, and RBX equals negative 20 kips. Be careful with the negative signs here. It's pretty easy when you've got a lot of negatives floating around, if you don't really carefully work through your algebra, to lose a negative, flip that sign, and end up with something completely different in the end. Just being off by a sign here will throw everything in the problem off. So RBX is negative 20. That means our assumed direction up here was wrong, which kind of makes sense if you think about pulling down at C. That's trying to pull this support away from the wall. So we need something to pull it in the opposite direction to counteract that moment. So the 20 kips there should be to the left, but we're stuck with our assumption here, and the symbol RBX is still negative 20. So when we go up to our x direction equation, we have to plug in negative 20 for RBX. So we have RAX plus a negative 20 equals 0. That means RAX is a positive 20 kips. So you might have to exercise some care in working with the algebra to make sure you don't lose negative signs, especially at this stage of the problem, since it has a big impact overall. But there we've got our reaction forces. So now we can go back to our original sheet here and draw our starting problem for the truss analysis. So I'm going to redraw the truss. We have our 20 kips force here, but now I'm going to draw in my reaction forces and draw them in the correct directions. So we had RBY was up with 20 kips of force. RBX was to the left with 20 kips. And RAX was 20 kips. This force right here was 20 kips. So that's what that looks like after the external problem. And we still have the same sizes here, 12 feet and 10 and 2. All right, so now we've got the external problem solved. We've got to jump inside the truss. And it helps if I label it correctly. A, B, and C. So to figure out what's going on here, we're going to have to jump into the truss and work on the joints. And it doesn't matter which joint you start with in this case, because all of them have only two unknowns. So it wouldn't matter if we started at A, at B, or at C. C looks like my last choice. And I'll tell you exactly why C would be my last choice to work out. Because both members are at angles here, which means I'm going to have to figure out two angles, and I'm going to have to work with sines and cosines of two different angles. And that just sounds like a mess. In fact, if you actually worked it out at C, you'd end up with a set of simultaneous equations to solve. And while we have the mathematical skills to do that, it's not something that I'd choose to do if I had other choices. You always want to pick joints that have members, at least one of the unknown members, horizontal or vertical. That means at least one of the members is going to not involve sine or cosine. So member A or member B, either one would be easier to work than joint C. And A is slightly easier than B because it only has one external force on it. It's got that 20 kips. So I'm going to go with joint A first here. So joint A will be the first joint I'd work out here, and I'll draw that one up here. Free body diagram for joint A. We've got 20 kips to the right. Then I've got this, I've got the force due to member AB, and it's not necessarily clear what direction that would necessarily be in. You can use a little bit of physical intuition in some of these problems and simpler ones to kind of figure things out. Like you might think, well, if I pull down hard enough on C, that's going to definitely push on A. So it makes sense that AC should really be pushing kind of down to the left like that. And now that you've kind of convinced yourself of that physically, it makes it a little easier to figure out, well, AB, the only way this could still be in equilibrium with the forces drawn as they are is if AB was up. So that looks like equilibrium. We've got a tug of war, no one's winning. In order to do the equations, we need an angle. We need this angle right here. And I usually prefer angles to horizontal. To get that out of the drawing, we got to be careful though. The technique I showed last time, which I'll show again here, works fairly easily. It does mess the drawing up a little bit, but that's okay. It's scrap paper. To be clear, you get the right angle, because at this joint, you could either figure out this angle here, you could figure out this angle here. Either one would work, but which one corresponds up here? It's not always easy to tell. So take the members and extend them out so that you've got a cross there. Now member AC is right here, and I'm looking for that angle right there. When you have a cross going, and you can draw the horizontal in here also, whenever you got lines crossing, the angles on the opposite sides are the same. So the small angle here is going to be the same as this angle, and I can figure that angle out by kind of building a right triangle here. I've got a right triangle that's 12 feet long and 2 feet high. Inverse tangent of 2 over 12 will give me that angle. So if I take 2 over 12 and inverse tangent, I get 9.4623 degrees. 9.4623 degrees. And that'll be the same angle up here, 9.4623 degrees. Pretty shallow angle. Now you could have certainly found the other angle here. You could have found the angle to vertical and used that. That'd be the complement to this, about 81 degrees or so, 80 and a half degrees. But either way works, as long as you've got that in the right place. I can't tell you how many times I've seen people draw this angle, but then label it with the complement. Label it with the wrong one, and that messes everything up. So be absolutely sure you've got the right angle. Sketch out anything you need to make sure that you've got the right angle in there. Once you've got that angle, you can go ahead and do your sums. So we've got our sum of forces in the x direction and our sum of forces in the y direction. In the x direction, we've got that 20 kips to the right, and we've got a piece of FAC to the left. So we've got minus FAC. We've got the adjacent piece to the left using that 9.4623 angle. So adjacent goes with cosine. So that's my x direction sum. For the y direction, I've got all of FAB up, but I've got only a piece of FAC down. And if I used the adjacent piece with x, it's got to be the opposite piece for y. So that's down, so it's negative FAC, and it's sine 9.4623 degrees. Now, since we're in equilibrium, both of those sums equal 0. Now, unfortunately, we can't solve the y direction equation just yet. We've got too many unknowns there, but we can solve the x direction equation. If we add FAC cosine of 9.4623 to both sides. Maybe I'll come down here and do that. We'll have FAC cosine 9.4623 degrees equals 20. Divide both sides by the cosine. And we've got 20 divided by the cosine of 9.4623. Cosine, there we are. And that's 20.276. So FAC is 20.276 kips. Came out positive, so our direction's good. And we'll figure out tension or compression here in a moment. Let's go to the y direction equation. We can solve that by plugging in FAC. So we have FAB minus 20.276 sine of 9.4623. And if you work that out, which is pretty straightforward, so we just take 20.276 times the sine of 9.4623. And that gives me 3.3333. So FAB is 3.3333 kips. Also positive, so we know that it really does pull joint A up. So let's see what that means in our table. Let's go and fill that in the table. We've got member AC, and I'm going to round these down to the right number of sig figs for my table. When I do my calculations at joint B, I'm going to use these numbers. I'm going to at least use AB, 3.3333, not rounded down to 3 sig figs. But just for presentation's sake here, I'll put that in there. So AB, 3.33 kips, and AC, 20.3. But now we need to figure out tension or compression. So let's look at member AB. Member AB is straight up and down. It is above joint A. So on our free body diagram for joint A, member AB looks like that. And if you have to draw out those pictures of tension and compression, tension pulls in, compression pushes out. So which one we have here? Well, looks like that's pulling in. So that's tension. Member AB is in tension. Member AC, joint A is down here. Member AC is to the right and up. So member AC is up here. And if we look at our drawing here, that looks a lot closer to what we've got with AC. So we have compression for member AC. And that fits with our physical intuition looking at the drawing. If we're pulling down on C, last time I said, imagine the loads get so heavy that the thing starts to deform or break down. Use your intuition and what it would look like as it fails to try to figure out whether something's in tension or compression. Well, if you pull down hard enough on C, that's definitely going to compress AC. But as it's compressing AC, it's also pushing joint A down. And since joint A is only on a roller, that roller is going to roll. And it's going to roll down the wall, stretching out AB, which is why AB is in tension. It's always good to go back and look at the physics of it, look at the drawing, look at the schematic, and make sure it makes sense. Because that'll make it really obvious if you flipped these up and you said, well, AB is in compression and AC is in tension. That'd make it a lot clearer, because physically it can't be that. And if it can't be physically right, then your math and your table can't be right either. All right, so one more joint to take care of. To get our final answer, we need BC. So I'm going to jump to joint B because I've still got something working at a vertical. Joint C is still ugly because of the two angles involved there. So let's draw the free body diagram for joint B. So for joint B, joint B's free body diagram, there's joint B. At joint B, I've got 4 forces interacting. I've got two 20 kip forces, one up and one to the left. And then I've got my two unknowns, really only one unknown because I know what's going on with AB. Member AB carries 3.3333 kips in tension. And if we go back to the picture here, tension means pulling inward. So pulling inward at the top here would mean pulling down. Remember, AB is in tension, so it's that stretched out rubber band. It's trying to bring the joints closer to each other. So joint B feels a 20 kip downward, or sorry, a 3.3333 kip downward force. And then we've got member BC. And again, drawing out what we know first gives us a pretty good clue as to what direction our unknown needs to be in. The only way that this could possibly be in equilibrium is if member BC pulled down like that. But in order to work out this equilibrium, we need an angle. And so you could either figure out the angle here or figure out the angle here. And since I did the vertical or the horizontal angle in joint A, I'll do the vertical angle in this one. So I want this angle this time. And that one's pretty easy to find up here. It's that angle right there. And we can build that up by building up this right triangle. Our opposite side is 12 feet. Our adjacent side is 10 feet. So we have the inverse tangent of 12 over 10, opposite over adjacent. So 12 over 10, inverse tangent. And we get 50.194 degrees. So that'd be our angle there. There we go. So 50.194 degrees. Now we've got our angles. We can do our equations. We only really need one equation in this one because we only have one unknown. And again, if I do the y direction equation, I've got to deal with 3 forces. If I do the x direction, I only have to deal with 2. So, I've said before, engineers, scientists, mathematicians, all of us are inherently lazy. We want to do things in as few steps as possible. So if we can look ahead for a second and kind of say, well, which path is going to be a little easier? Not always right, but it usually works out. You can figure it out by looking at it. So here in this case, x direction equation would be where I'd go. So I'll do my sum of forces in the x direction. I've got negative 20 kips, and then I've got the horizontal piece of member BC. Well, the horizontal piece is the opposite side with the angle I've got there, and opposite goes with sine. It is to the right, though, so it's positive. So it'd be positive FBC sine of 50.194 degrees. And that's equal to 0, and we can solve that. If we add 20 to both sides, we'll have FBC sine of 50.194 degrees equals 20. Divide both sides by the sine of 50.194, and I'll leave that the details of that to your practice on that one. I'll just divide it out on my calculator. Sine of 50.194. Sine, there we go. Divide, I've got FBC is 26.034. That'd be kips. Came out positive, which means our assumed direction was right. And at joint B, member BC is down and to the right. So member BC is right there. So we could look at our cheat sheet here. Pulled inward. Looks like what we've got there. That's tension. So member BC is in tension, and I can round that off to 26.0 in tension. So there we go. Came out positive, so we know our directions right. And usually with simple trusses, we can guess the directions almost 100% of the time. If you end up with a negative answer, the easiest thing to do is figure out whether it's tension or compression as if it came out positive, and then flip it. So if my answer came out negative 26.034, I'd probably still look at this and say, well, if it was positive, it would be tension, but it's opposite that, so it must be compression. So that's easier than trying to redraw the drawing and flipping things and then reinterpreting it. Reinterpret what you've got and then flip it if you get a negative answer. So there's our answer, final answer to the final number of sig figs. Any questions on that one?
Nope. Do we gotta do a summary?
You don't have to do them. It's good to do so. I was not going to do that just out of interest of time, but it's not a requirement. It's just about communicating your results. So I would say at a minimum, you'd need either the table with everything rounded to the right number of sig figs, or you'd need a summary diagram. It can be helpful usually in these problems, like when I have them on the exam. Usually I'll provide you with a table, and then all you really have to do is have that table filled out. Now, it would be good to have your supporting work available because I might not have a place to say where your reaction forces are, but that's certainly worth a chunk of the points, is figuring out those reaction forces at the support. So it'd be nice if I could find that somewhere. But if all you give me is the table and those numbers are wrong, that's a huge amount of partial credit that you lose. So the more information you can give and the better you can communicate your results, the better. But I would say at a minimum, either a table or a force summary diagram.
All right.
All right. Well, let's take a break for a few minutes here, and we will come back, and I'll put a couple of truss problems to work out up on the page for you.
All right. I might not come back just so I got a test in the morning.
Okay.
But I'll go back and watch the video later.
All right. I'll put one up, and we'll work through it. All right, so next time we'll be moving on from method of joints to look at method of sections. Method of sections is another way of looking at solving truss problems. It has one big advantage in that it doesn't require that we solve everything in the problem. If we have a very large truss with lots of members, it would be extremely tedious to solve by method of joints. We can jump to method of sections. That lets us jump right in the middle of the truss rather than working across it from one side to the other or working from the outside in. So we'll see how that works. So let's go ahead and look at a practicum problem. All right, here's our practicum problem for the evening. And this is a fairly realistic problem here to find the loads and states and tension and compression for each of these members. And we have, let's see, 1, 2, 3, 4, 5 members to work with there. This is reasonably common kind of roof truss setup. In fact, it's something I have in my attic, and it's got a 24-foot span down here at the bottom. So the walls that it's supported on, these happen to be over my living room. We have 24 feet going across, and then it's about a 6-foot height. I know when I stand up there, I can just barely stand up, and I'm just a little bit under 6 feet. So there's about a 6 foot height there. And it's not quite a traditional roof truss, but it's something people used to do in the 40s and 50s when they built these large spans. It's a 12 foot, 24-foot wide span, and it's got this little, it's got this member dropping down here from the apex to tie right into the middle, so that it can go across the span without this joist sagging too much. It wouldn't meet code today in a for a 24-foot span using this kind of lumber, but it back then people did it pretty routinely. So let's go ahead and analyze this. We'll figure out what the loads are. If I have 10,000 pounds of force put right on the apex with a 6,000 pound side load. So we'll figure out what the states of tension and compression are. The first thing we have to do is solve the external problem. Here we've got lots of steps, so got to be careful to control round off error. So we want 4 good sig figs in our answer, so we're going to need 6 when we round off. So anything we round until we're done with the problem, we're going to round to 6 sig figs. So let's do the external problem first. So we'll sketch a free body diagram. We don't really need any of the details of the internal structure of the truss to solve the external problem. We just need our externally applied loads and our support forces. So here at joint A, I've got RAX and RAY. Over here at the other end, which I've labeled joint C, we've got a roller. So we've got RCY coordinate system. And we'll copy the geometry off of the problem as we need it, off of the original drawing. So we've got a non-concurrent force system, so we're going to get 3 equations. We have our sum of forces in the x direction. There we've got a positive RAX and a positive 6 kips. For our sum of forces in the y direction, we've got a positive RAY, a positive RCY, and a negative 10 kips. For the moment equation, I'm going to pick joint A for my moment equation. So I'll take my sum of moments about joint A. Let's figure out which forces will have moments and which ones won't. Definitely RAX and RAY are out. RCY will definitely have a moment. The 10 kip force, its line of action's over here, well away from A, so it will have a moment. And so will the 6 kip force. Its line of action is pretty far away from A. So we're going to have 3 terms in our moment equation: RCY, 10 kips, and 6 kips. Now, the 10 kip force, its line of action's right down here through the middle, and according to our drawing, that's 12 feet from A. So we have 12 feet times 10 kips, that's 120 kip feet. If we pin at A and push down at D, we'll get a clockwise moment, and clockwise moments are negative. We've got that 6 kip force. The line of action for that 6 kip force is right there. And the closest it gets to A is 6 feet. So we have 6 kips 6 feet away. That's 36 kip feet. If we pin at A and push to the side at D, that's still going to be a clockwise rotation. So negative. And then we've got RCY. RCY is 24 feet away. So we have 24 RCY. If we pin at A and push up at C, we get a counterclockwise moment. Counterclockwise moments are positive. So there we've got our 3 equations of equilibrium. We can solve those. RAX is a negative 6 kips. So that means we assumed the wrong direction for A. For RAX, it needs to be to the left, not the right. We can't do anything with the y direction equation, but we can work with the moment equation. Moment equation, we've got negative 120 minus 36, that's negative 156, plus 24 RCY equals 0. 24 RCY equals a positive 156, so RCY will equal 156 divided by 24, which is 6.5. So 6.5 kips. Notice if you forgot the arm for RCY, you'd say RCY is 156 kips. That's way higher than any of the forces that are applied, and that's the first clue that you've forgotten the arm in your moment equation. If you get way too big of a number, so maintain your situational awareness of the problem. Maintain some idea of what numbers are reasonable and what aren't. If you're only pushing on this thing with 10 kips and 6 kips, you shouldn't expect hundreds of thousands of pounds coming out on the supports. And if you get that, you should immediately flag it as unreasonable and figure out what went wrong. So 6.5 kips is what we get there, and that's RCY. So we have RAY plus 6.5 minus 10 equals 0. And if we solve that, and I won't belabor the solution here, I'm going to assume that everyone's feeling pretty confident with algebra at this point. RCY comes out to be 3.5. And that's also kips. So good news, no rounding so far, so we haven't lost any accuracy. We've got our external forces. So let's redraw the drawing here a little bit. We've got at A, we've got 6 kips to the left, and we've got 3.5 kips up. We have 6.5 kips up there. We've got 10 kips. And we've got 6 kips. All right, so that's what the external problem looks like. Now we need to jump inside the truss. We need to figure out what's going on at our individual joints. So we've got A, B, C, and D. And to do that, we need to isolate a joint. We need to pick a joint to work with, isolate it, draw its free body diagram, and solve for the 2 unknowns at most that it'll contribute. We can expect, since I have 4 joints here, I'm going to have to work out 3 of them. And of those 3, just kind of formulating a plan of attack for the problem, I would probably work A, B, and C, just because those involve things that are at least at horizontal or vertical. D looks ugly, not just because there are potentially 3 unknowns there, but because we've got 2 angles. Now, granted, we've got some symmetry in this problem, so it's not so bad, but it could easily be slightly different than that and then be asymmetric, and we'd have a lot more work to do. So let's draw our table up here. We've got 5 members to work with: tension, compression, load, and kips. And we've got our members. So we'll have member AB, we'll have member AD, we'll have member BC, BD, and CD. So there we've got our 5 members. So let's start, let's start at joint A. So we need the free body diagram for joint A. So if I draw my circle around joint A, I've got 4 forces. I've got the 2 reaction forces at the joint, at the pin, and then I've got AD and AB. Always start with what you know. So I know for sure the 3.5 kips is up, and the 6 kips is to the left. And see how your solution for that external problem is immediately coming into play here. So if you screwed up your external problem, you've got no chance to solve the internal problem correctly. So it's worth taking a look back at the structure and making sure that your answers seem reasonable. And sometimes it's easy to do that by just sort of playing with the numbers a little bit. If you ignored that 6 kip force for a moment and just imagined that 10 kip force there, we'd have symmetry. And with symmetry, we have even distribution of forces. If we could flip the thing back and forth and it looks the same, then it's got to be the same forces on both sides. If we had 10 kips pushing down at the apex, we'd have 5 kips on the left and 5 kips on the right. We'd have no side forces. Well, those 5 kips on the left and 5 kips on the right get offset a little bit because of the 6 kips pushing to the side. Because when you push to the side here, you're trying to make this right hand side dive down while you're picking up the left hand side, trying to rotate everything like that clockwise. So that lowers from 5 kips the force at A, the vertical force at A down to 3.5, and the horizontal force or the vertical force at C makes it go up by up to 6.5. So these look pretty reasonable. Looks like it'll make sense. So we've got a pretty good chance of getting the right answers here. Member AB, we've got to represent that in here in our free body diagram, and it looks like the easiest way to do that is to draw it as a pulling force. So we'll call that AB. And then the only other reasonable way to go for AD is to go down and to the left. Member AD. We're going to need an angle, and I'm going to want this angle right in here. That's going to be the same as this angle here. If you draw the members out, you can see kind of where that bottom, that left-hand side of the cross is. It's got to be the same as this angle. And we've got a right triangle here. This is 6 feet high and 12 feet wide. So we have inverse tangent of 6 over 12, which is 26.565 degrees. And because we've got symmetry here, the other side's going to be the same. So we've got 26.565 degrees there. So there's our free body diagram for joint A. We can do our sum of forces in the x direction and sum of forces in the y direction. In the x direction, we've got all of AB. We've got minus 6 kips. Don't forget about that one. It's easy to lose that, but keep in mind the forces you got. You got 4 forces here. That's not just a horizontal reference line. That's 6 kips of force. And then we're going to catch a piece of AD, the adjacent piece, the cosine piece. So that's to the left, so it's negative FAD cosine 26.565 degrees. Then we've got our sum of forces in the y direction. We've got 3.5 kips up, and we've got a piece of FAD down. It's down, so it's negative FAD. And then we need the other piece, the vertical piece, the opposite piece, the sine piece. So sine of 26.565 degrees. So there we have our sums in the x and y direction. So we set those equal to 0 because we've got equilibrium. We can't solve the x direction equation, too many unknowns, so we'll go to the y direction. And this should look pretty familiar so far. You'll see lots and lots of these, so get used to solving them. If we add FAD sine 26.565 to both sides, we get FAD sine 26.565 equals 3.5. Divide out the sine. And we've got 3.5 divided by the sine of 26.565. That's 7.8263. So FAD comes out to be 7.8263 kips. Came out positive, so we know our direction's good, and we can pretty easily, and we'll be able to interpret our tension or compression from that. Knowing that FAD is 7.8263 kips, we can go back into our x direction equation. So we have FAB minus 6 minus 7.8263 cosine 26.565 degrees. And I'll trust you to work that out on your calculator, but without going through the steps of the algebra. 7.8263 times the cosine of 26.565. And that gives us a little tiny bit more than 7. So 7 minus 6. So it looks like FAB comes out to be 13.000 kips. And we were looking for 6 sig figs here, so I guess I've got to go back and fix that. Let me see how much that changes. So because we needed 4 sig figs, a little too used to doing 3, I suppose. So if we do 6 and 12 inverse tangent, 26.5651 is where those angles come out to be for sig figs. And 3.5 divided by 26.5651 sine 7.82622 to 6 sig figs, and 26.5651 cosine times, and add the 6 in there. We have 12.99998, which rounds to 13.0000. So not much of a change there. So both of these came out positive. So what's that mean for tension and compression? Well, compare joint A in the physical drawing to joint A in its free body diagram. Member AB is to the right of joint A. So member AB is over here. Force on AB, we determined that was positive. So our direction's right in our free body diagram. So member AB is pulling joint A inward. That's tension. Members in tension are trying to shrink back to their original size. So they're pulling the joints toward the middle of the member. So member AB is in tension. So we can go to the table, we got tension there, and we can round to our 4 sig figs here, 13.00 for that. As long as we don't use that in the calculation, it's fine. We'll use the full format ones in the calculation. Member AD, we had 7.826. And according to our drawing, member AD is up and to the right. So member AD is over there. Member AD is pushing joint A away. So member AD must be in compression. Only members in compression push the joints outward. So member AD, we can check the compression box on that. So there we go. 2 of the members down. So let's move on to the next joint, and I'd go to joint B next on that one. Joint B looks pretty simple since everything's at 90 degrees. Now let's see what the free body diagram looks like then. So if we go to joint B, there it is right there. We know one of the forces at joint B. We know what member AB is doing. So member AB is in tension, and members in tension pull their joints inward. So A went to the right, B goes to the left. So joint B feels a force to the left of 13.0000 kips. So it makes sense that member BC is probably exerting a force to the right. So we'll put member BC. We got 3 forces there. Member BC, we'll put that into the right. And then we've got member BD. And you might look at member BD and say, well, it looks like it's getting pushed down on by this 10 kips force. So maybe by the time it gets down here, it's also pushing down. So that might not be a bad way to draw it. So we do FBD. So there's our free body diagram for joint B. Well, let's do our sums. We don't need any angles here because everything's at 90 degrees. If we do our sum of forces in the x direction, we get negative 13.0000 plus FBC. Now that equals 0, and so obviously member BC must carry 13.0000 kips. What about the y direction equation? Sum of forces in the y direction, we've got nothing up and we've got member BD's force down. Well, this is equilibrium, so whatever that sum is, no matter how simple that sum comes out to be, even if it's only one term, the sum is 0. Well, the only way FBD can satisfy this equation is if it's 0 too. Member BD is unloaded in this configuration. So member BD carries no load. So FBD 0. So we can take that to the table. Member BD is 0. We'll go back and look at that here in a second. Member BC came out positive, so we can trust the direction we've drawn. According to our drawing, member BC is to the right, so member BC is over here. It's pulling joint B toward the middle of the member. Pulling is tension. So we have member BC carrying 13 kips, also in tension. So rounded 13.00 in tension. So let's look at the kind of mystery here. Why is BD unloaded? Well, when you're working with the joints, all that matters is what connects to those joints. And if you look at member BD's connection here, all you've got is the connection here at the top, BD's force, and then you've got these other two, the AB and BC. Well, AB and BC are horizontal, so they're going to cancel each other out. There's nothing for this to apply force to. Now, the situation would be different if I hung something from B. If I exerted a force at B, then there'd be a vertical force for BD to react against. And you might still be thinking, but what about that 10 kips up at the top? Well, you can't always assume that the force just goes right through and pushes on what you think it'll push on. There are other members interacting here. There's AD and CD. And whatever happens with AD and CD, they must be exerting enough force right at D so that it opposes that 10 kips pushing down, so that BD isn't really needed for any of it. So let's do our final, or take our final joint here at C, and I'll just draw that one right on this one here. So joint C is our last joint, so we're only going to have to do one equation. Let's set up the free body diagram. We've got 3 forces interacting there. We've got our reaction force that's 6.5 kips. We have BC, which is in tension. So since it's in tension, it's pulling the joints together. So B was pulled to the right, so C has got to be pulled to the left. So that's 13.0000 kips. And then we've got to figure out what's going on with CD. Well, the only thing that makes sense is if CD pushes down and to the right there. FCD. And we already know that angle. It's the same angle right there. That's 26.565. 1 degrees. So we only need our sum of forces in the x or the y direction. Since I calculated the 13 kips, I'm going to discount that one a little bit in priority, and I'm going to take the 6.5 kips instead. Even though I calculated that, it's closer to the original information. So it hasn't gone through a couple other calculations. So chances of error are lowered if I go to something closer to the original information. So I'm going to do the y direction equation here. Sum of forces in the y direction, we've got a positive 6.5. Then we've got a piece of FCD down. The piece that's down is the opposite side. Opposite goes with sine. So we have sine 26.5651 degrees. That's equal to 0, and that's a similar setup as we've solved before. Divide both sides by the sine. And what do we get here? So we've got 6.5. We've got the sine of 26.5651. And that gives us 14.5344 kips. So that's what member CD carries. And according to our drawing, joint C is there, member CD is up and to the left. So member CD is pushing joint D away. Only things in compression can push things away. So member CD, to fill in the last line in our table, 14.53 kips in compression. Now, if we look at the truss, this is how it usually works out with things like roof trusses and a lot of trusses out there, like bridges and such. The tops tend to be in compression. The top core or the top parts of it tend to be in compression. The bottom tends to be in tension because when you push down on the top of this, think about a ladder. If you had a ladder on a slippery surface and it didn't have those cross pieces in there, like a step ladder opened up and you didn't have those stabilizing or safety cross pieces in, if you push down on the top, the thing's going to splay out. The ends are going to go away from each other and the top's going to collapse. And that's exactly what this is trying to do. When you push down at the top, this whole thing's trying to flatten out. Well, the bottom cord of the truss is what's holding against that. And so as the ends are trying to be pushed away from each other, that's pulling on this bottom cord. And that's exactly what happens in a lot of roof structures. The walls are what we're sitting the roof on top of. The joists or the bottom cords of the truss, depending on what your roof structure looks like, that structural element is there to keep the walls from spreading apart. If we didn't have those there, and this happens if you're familiar with residential construction, you might be familiar with things like cathedral ceilings, where people try to build a ceiling that kind of goes up to the top. Well, if you don't get that exactly right and you don't have enough structure there, things like snow loads and forces pushing down can actually push the walls of the building apart. And my father, who used to do some building inspection on the side, he told me once, if I was ever looking at a house that involved a cathedral ceiling, take a big level, put it against the walls on the outside, and make sure those walls aren't being pushed apart. So it's that cord here, that bottom piece, what they call the bottom cord or the ceiling joist, is what's holding those walls together. So those are usually in tension. Now we can see here we've got a little bit of imbalance in it. Member AD has less compression than member CD. That's because of the side load. When that side load is pushing on it, it's squeezing more on CD and it's pulling on AD. Not enough to put AD into tension, but certainly enough to break the symmetry and unload it a little bit from the 10 kips that would otherwise be part of what's pushing down on. So by looking at the structure, we can see a little bit of a physical explanation for why we get the answers we do. And you should always go back and make sure that your answers look reasonable. All right, so that's about as complex as we get for method of joints kinds of problems. Anything more than this ends up taking a lot longer to work out. You do have a problem on your homework assignment that is going to take a little while. It's got a lot of members in there, so it's the last problem on there. So take some time with that one. Be careful, because an error at almost any stage can throw off all your subsequent results. But as far as what I'd expect you to do on something like a quiz or a homework assignment, it would top out right around here. The problems we've been doing. Uh, all right, so next time, method of sections. Have a good night.